Hi, welcome back to another episode of Algebra in Words, the video series on YouTube. In this episode, we're going to start looking at rational expressions, starting with just adding and subtracting rational expressions. Now, what I have on the board here is rational expressions versus rational equations. And it's very important that you know the difference, which I'm going to get into in a minute or two. Before we get started, I want to let you know that if you prefer to read along with what we're going to go over today with readable examples, you can follow along with it in my book, Algebra in Words. You can find the link to that on Amazon in the description box below. And what we're going to start on rational expressions starts on page 106 of the book. Okay, so before we start, the subject of rational expressions can be a little bit all over the place. Now, first of all, what are rational expressions? Well, if you start with the root word rational, or you think of ratio, it's basically fractions with variables, okay? And you see that I have a simple problem of adding two fractions, something that you probably are more familiar with from when you did fractions back whenever that was. So I'm going to use this and do a quick little refresher of that to segue us into adding rational expressions and basically to show you how similar they are. Now, as I was starting to say, when we get into the subject of rational expressions and equations, it can be a little all over the place and misleading. Now, what happens at first is, usually in any textbook, you start by adding and subtracting rational expressions. What are expressions? It's terms that you can manipulate or simplify or factor and rearrange in some way, but there's no equal sign. So it's not technically an equation. You're not solving for x. But in a rational equation, it's an equation that has rational expressions or ratios with variables in which you ultimately do solve for x. Now, here's the thing about that. Usually you do rational expressions, addition and subtraction of them first, and then you segue into rational equations. But the problem is that when you get used to the method of adding and subtracting rational expressions, that's not the method that you use for solving rational equations. And it can be a little confusing at first when the difference between this and an equation is just equal to, and it could equal another fraction, or it could just equal 0. I wanted to make sure that I come right out and say that first before we get into explaining both types. In this video, we're going to strictly focus on adding and subtracting rational expressions. In a later video, I'll dedicate that just to rational equations, and I'll probably have multiple videos or at least multiple examples of that, because even that can be broken down into two different types. So anyway, without further ado, let's get started on adding or subtracting. In this case, it's adding rational expressions. So to start, I have a simple expression of just two fractions. So what we're going to do is to just add these two fractions. We have 1/9 plus 1/12. Now, if I were to ask you, are these fractions alike? The answer is no. Why are they not alike? Because the denominators are not the same. And in order to add or subtract fractions, they must be like fractions, meaning they must have common denominators. But these are not common, so we need to make them common. So we're going to go for making the least common denominator and go from there. So a quick little flashback, and I did cover factoring in a previous video. You can find that link to the list of that in the description box below. But anyway, we are going to do old school prime factorization of the 9 and the 12 for reasons you'll see. So let's just do 9, and that breaks down into the prime factors of 3 and 3. So I'm going to show that like this, and also in exponential form as 3 squared. And then let's also look at 12. 12 can be broken down into 3 times 4, and the 4 can be broken down into 2 times 2. And finally, so let's just write 3 times 2 times 2, But if we write that in exponential form, it would look like 2 squared times 3. And for now, I'm just going to say to the power of 1 because I want the exponent to be there for now. Now, if you remember how to find the LCD, you take all the factors of one of the terms, so let's just start with this, and we're going to automatically take 3 squared, but we're also going to compare to the other factors from the other term that we prime factorized. And here's how it works. You take all of the bases, no matter what. But if there's repeats of bases, then you take the higher of the exponents. So for example, this is 3 squared, but this also has a base 3 factor, except this is 3 to the 1. So which is higher, the power of 2 or the power of 1? The power of 2. So we're going to put 3 squared in our LCD. And now we're going to come over here and we have a 2 squared. Now this doesn't have 2 or 2 squared, that's fine. You take all of the factors, and if there's repeats, you take the higher exponent, but there's no repeats, so we just take 2 squared. Now I'm going to show this. This is an exponential form because we were looking at the highest exponents, but we could also look at it as 2 times 2 times 3 times 3, or if we multiplied it together, we could think of it as 36. And those are just all different variations of the same LCD. Now we're going to, let me erase the prime factorizations here so we have some room, and then we're going to apply that to adding the 2 simple fractions. So the next order of business is we want to convert each fraction, if necessary. It won't always be necessary, but we're going to, in this case it is, convert each fraction into like fractions, meaning common denominators. So how are we going to do that? Well, what I like to do is, we already know the common denominator is going to be, the least common denominator is going to be 36. So let's just put that to the right of the equal sign in the denominator, and we'll fill in the top as we go. But we need to properly convert the fractions, and here's what you need to ask yourself. Look at the 9, right, and say to yourself, what factor of the LCD is missing from the 9 to make 36? And the answer in that case would be 4. So we're going to, let me change color marker, we're going to multiply the top and bottom of each fraction, well, the top and bottom of this fraction, by the missing factor 4, because 4 times 9 makes 36. Alright, and so right now we're going to we are going to just write 4 over 36 because this fraction now became this fraction. Okay, and it's plus, so write plus. And now we're going to convert the 1/12. And we're going to apply the same method. Look at the 12 and compare it to the 36. What factor of the 12, what factor is missing to make the 12? 36. And the answer in that case is 3. So we're going to multiply the top and bottom of this fraction times 3 like this. And now, here, we're going to write what that becomes converted. 3 times 1 is 3, and the 12 times 3 is 36, which is what we intended it to do. Now we have like fractions because we have common denominators. And now we're going to apply the function, the operation across the top, adding the 4 plus 3 over the least common denominator, now 36. And that's 4 plus 3 is 7, so the answer is 7/36. So that was a little refresher of adding simple fractions to get us prepared for adding or subtracting rational expressions, which is basically fractions with variables. Okay, so take a look at that. If you need to look it over, pause the video, but I'm going to erase this and this so that we have more room to do the top expression now, using basically the same method with a little bit more. So now we're going to start on adding our two rational expressions. Now, what we want to do first in this case is, let's just look at an overview. Once again, the goal is to make like fractions, meaning we want to have the least common denominator, and we want both fractions to have the same denominator. That's the least common denominator. We are going to convert each fraction by multiplying the top and bottom of each fraction or rational expression if necessary. Sometimes we'll need to, sometimes we won't need to. But the only way to find out is to first factor all numerators and denominators, mainly the denominators, see what factors we get, then we'll evaluate those factors to determine the LCD. Also, one thing that I highly recommend to you as well as to my students is to, and it may seem insignificant, but it's helpful, is to always put parentheses around binomial or polynomial factors in the denominator or anywhere. So we're going to do that here. It's really more important for this factor for the reason you might see in a second. So let's just take a pause and look at the strategy we're going to use. We're going to factor all the denominators. Then from those factors, we're going to create and determine the LCD, the least common denominator. Then using that, we're going to convert both fractions if necessary. Do the conversions. Then we're going to add them, because this is addition. We're going to add the numerators together. We'll distribute if necessary. We'll combine like terms where necessary. And then basically we'll reevaluate it from there. Alright, so first of all, let's look at that trinomial. Can that be factored? And the answer is yes, into two binomial factors. And those two binomial factors could be x minus 2 and x minus 5. How do we know that? Because, first of all, this is plus. That tells us that these signs will be the same as the middle sign of this, which is negative, so they're both negative. And then if we look at the factors of 10, 5 and 2, and they both, if we put them both in here, and we FOIL it just to check, product of the first is x squared, product of the outside is negative 5x, product of the inside is negative 2x, and negative 5x minus 2x is negative 7x, so that works. And finally, negative 2 times negative 10 is negative 2 times negative 5 is positive 10, so we chose the right factors. And I'm just going to do this just to show that we factored this and that these are now the factors in the bottom. Okay, so now let's look at the factors in the denominator. And now you probably see why I wanted this in parentheses, because it looks more like a binomial factor, as opposed to just two loose terms. So, the LCD, let's do that here for now, is going to be both of these factors, and we could think of this as the quantity x minus 2 to the power of unwritten 1, and this factor, x minus 5, also to the unwritten power of 1. And now we have this one too. So question is, do we add another factor into this and make this x minus 5 squared? And the answer is no, because it's a repeat, and since this is the group to the power of 1 and this is the group to the power of 1, we don't need to add it a second time. We would only choose the factor of the higher exponent, but neither of these is higher. So it's just a repeat, and we just leave it as this to the power of 1. Alright, so now we have our LCD. This binomial times this binomial. And now we're going to try to apply that to the fractions above. So, we're going to compare the denominator here to the LCD. And does this denominator's factors have any missing factors compared to the LCD? No. Coincidentally, no. So we don't need to do anything to this rational expression at all to convert it. It's going to stay the same. However, when we look at this fraction, does this denominator have any missing factors compared to the LCD? And the answer is yes. It is the quantity x minus 2. So we're going to, just like in the last example of regular fractions, we're going to multiply the top and bottom times the missing factor of x minus 2. Alright, and sorry that the equal sign is in the way there. Let me get rid of that for now, just to make it more room and not confusing. And so now, what we're going to do is rewrite this fraction. It's going to look like this. 6 over x minus 2 times x minus 5. And I'm going to now extend this over because now we have the common denominator for both fractions. It's this times this. We're going to bring the 6 over from the left. We're going to write plus from here. And now we're going to distribute the 3 through the group x minus 2 and write what that equals here. So 3 times x is 3x. 3 times negative 2 is negative 6. And we're going to continue to simplify mainly in the numerator. So let me come down here. And now we have 6 minus 6. That cancels out to 0. So the 6's are gone, leaving only 3x in the numerator. And in the denominator, we have x minus 2 times x minus 5. Now normally the last step is always to, after you've combined like terms and simplified in the numerator, the next step is usually to check to see if there's a greatest common factor. If there is, factor it out, because that might reveal other factors in the top and bottom to be factored out. But in this case, there's no factor, this can't be factored anymore, nor can this factor with any factors in the denominator. So this problem is done. So there we go, one problem on adding or subtracting rational expressions. Before I end the video, the adding or subtracting of rational expressions is the same whether this is plus or minus. The method is the same. The only difference is that if this was minus, we would have to keep the negative sign with the numerator and distribute it through if necessary. But anyway, that concludes this video. I'll be going over more problems with rational expressions in another video. Thanks for watching. If you found this helpful, please give a thumbs up. Please subscribe to the channel. Please share with your friends. Leave any feedback in the comment section below. And also hit the little bell so you can be alerted when new videos come out. Also check out other content on Facebook and Instagram. And I'll see you in the next video.